Evening, everyone. So welcome to tonight's talk, Plant-Based Passive House, brought to you by Tab Binding and ACAN and various others. So I'm Tom Graham. I am one of the four coordinators of the ACAN Natural Materials Group, which is one of the 9 themed groups that make up the Architects Climate Action Network. And I'm just going to give you a quick introduction to ACAN. So ACAN is a voluntary group of architects, builders, engineers, students, and organizations working broadly in the construction sector. It was founded in 2019 with the desire to bring the activism of Extinction Rebellion to the world of architecture and construction. An autonomous collective believing in bottom-up organization to bring together people who felt that mainstream institutions weren't addressing the clear problems in front of us. So ACAN is now a global network of several thousand people responding rapidly to the climate and ecological emergencies that we have the displeasure of finding ourselves in. We have a manifesto with three aims here up on your screens. Decarbonize now. So we seek to radically transform the regulatory, economic, and cultural landscape in which our built environment is made, operated and renewed in order to facilitate rapid decarbonisation of the built environment. Ecological regeneration. We advocate the immediate adoption of regenerative and ecological principles in order to green the built environment, prioritise communities and ecosystems at threat, and promote the recovery and restoration of natural environments. And cultural transformation. We call for a complete remodelling of our professional culture. We must challenge and redefine the value systems at the heart of our industry and education systems. We seek to operate an open network to share resources and knowledge to aid in this transition. So ACAN is divided or has 9 working groups based on the themes on this page here, which obviously naturally overlap at times. So circular economy, education, embodied energy, existing buildings, climate literacy, urbanism, professional standards, ecology, and natural materials, set up by Janna in 2019, I think, at the early days. Yeah, she'll be speaking to you about her her work tonight. But so we have each group has open WhatsApp groups, and there'll be joining links for these coming into the chat during the talk tonight, if you'd like to join in any of these conversations. As well as this, we have StuCan, the student network of ACAN, headed up by Joe Bass, which operates, as you can see, across the UK, universities and educational arenas. The network aims to increase student agency, to unite student voices, and to create the cultural transformation, embedding ACAN's core aims in the curriculum. On top of that, ACAN International. We operate all across Europe, in Africa, in Australia, and if there is a country there that you are in and there is no ACAN group, then set that up, and ACAN will help you with that. So yeah, ACAN's actions take sort of a bunch of different forms. We so from campaigning, lobbying, and the creation of resources and content, Very much right now, the ecology group have put together a public statement on the planning, sort of the rather shocking planning and infrastructure bill. The existing buildings group have developed the UK demolition map, which is a sort of crowd-sourced map of buildings at threat of demolition. And the again, the same group, existing buildings, hug the building event in coming up in May. And what have we got here? And sorry, the climate literacy will be hosting their material donut workshops at Buildfest UK in July. So you can see busy. The other sort of angle to a lot of our actions is the provision of resources. And natural materials group we've just put together, or about to go live with. I think I've chopped off the website address off the top of that thing, because it's going to be big announcement shortly, with our natural materials details website with free downloadable details demonstrating natural construction. So the sort of things you're going to be seeing tonight from Seb, Janna, and Andy will be detailed on that website. But anyway, that's too much natural materials. So ACAN though is reliant on its membership to support its activities and continue its mission to change the built environment, the way the built environment is produced, and to produce the content, to produce the campaigns that we do. We have great reach. We have thousands, 10,000, over 10,000 followers on Instagram, over 10,000 followers on LinkedIn, 2,000 YouTube on the YouTube channel. Another great resource. But all of that is reliant on membership. So if you want to become a member, the link is on the website, and that the link to the website will be on the in the chat during the presentation. So that is ACAN, and I'm going to hand over to Tab for tonight's talk.
Long-term member of ACAN, as I myself, but tonight I'm here representing the Passivhaus Trust. Janna will do a quick introduction, obviously herself, with Grain Architecture, Seb Lomas from Archetype, Andy Hales again from Grain Architecture, and Jonathan Davis, who's going to do the question and answer. So please put your questions in the chat. So I don't know how many of you know about the Passivhaus standard, but the Passivhaus has principles of approach. It has 3 of them. It's clearly defined in detailed performance and comfort criteria. Every Passivhaus project must be modelled using the Passivhaus planning package. Quality assurance is delivered through careful verification at every stage. And together, that adds up an integrated approach. So Passivhaus buildings are based on fundamental principles that must form part of that integrated approach. There are Passivhaus building principles, of which there are 5. High-performance windows. High-performance continuous insulation with no gaps, a continuous high-performance airtight layer, and minimising of thermal bridges, and quiet and efficient mechanical ventilation with heat recovery, which is MVHR. Passivhaus brings multiple benefits. It brings building performance. It answers a response to the climate emergency. It brings health and well-being to the inhabitants. It helps people to perform better. It is kind to our pocket in energy consumption. And it brings social benefits. QR code links to our Passive House benefits, which I think there is 52 of. Is everything, can anything be called a Passive House standard? No. It might meet of some of the principles, but unless it meets all of them, is designed through PHPP and is quality assured, it is not a Passive House. If you want to know more, you can join us for our How to Build a Passive House series. We, on 7th of May, we're going to look at MEP and transferable lessons on the 4th of June. We'll put some links in the chat. And we have a new learning hub where you can have guided learning, there's guidance, there's reports, there's courses, and lots more. Again, I'll put a link in the chat. And I'd just like to say thank you for joining us tonight, and I am going to hand over to Janna.
Hi, Tab. Hi, everybody. Thank you all for being here. I'm just going to share my screen and let's hopefully, where is it? There it is. Okay, so yeah, we're obviously here to talk about our house, which is Llama-Croft, a plant-based passive house. Just a little bit more introduction, sorry, before we jump straight in, but I'm here wearing multiple hats as well. Obviously, as Tab and Tom have said, I've been part of ACAN as well, but I'm also Grain Architecture is the company I founded in 2015, so nearly 10 years ago, and yeah, we as a practice specialize in low carbon building with natural materials, so I have a background in that, and just to run through a few things that we do as Grain Architecture, we've got many projects on that we've done or are doing, from extensions, deep retrofits, working with listed buildings, through to community new build projects. This one needs more funding, so please give to Tuppenny Barn. Shout out. Yeah, self-build projects, off-grid self-build, straw bale. Sort of, this was like a course-led. What's the word? It was run as a kind of educational build, and many more. So that's the kind of, yeah, that's Grain Architecture. So my colleague Andy is going to talk more about that, because he's actually been wearing the sort of architects, the delivery architect's hat for our own project. So the design of our house is something I've been working on for a very long time. In fact, probably I was about 6 years old when I started thinking about my dream house, and became a bit obsessed, and I think it's been a pretty lifelong obsession since then. So yeah, it's quite amazing to now be at the point when we're sitting in it, which is very cool. But yeah, so it started a long time ago, and I've been working on this design and really trying to refine it, and I'm, as I say, quite obsessed with it, have been in getting a nice sort of simple layout, which I'm very happy with. And yeah, so one of the key principles, as Tab was mentioning about Passive House, is that it's continuous insulation, and also the form factor needs to be quite efficient, so not too large a footprint for the volume, area for the volume. So yeah, this house, when I was 6, obviously I didn't know about Passive House, and for many of the years that it was under sort of development, I didn't really think of it as a Passive House, but I always wanted it to be an efficient sort of house that was kind of quite independent and self-sufficient. So then came along Seb, who I met while studying at CAT, the Centre for Alternative Technology, and Seb works at Archetype, he'll introduce himself, but he's a passive house designer as well, and basically said that it would be okay for me to design our house on the premise that it is a certified passive house. So that's what we set out to do. So I had the design before the site, which I know is not the right way around, but I've been looking for a long time to find the right site, and this is what we found. And we bought this place in 2022. We're lucky to have found it because it's within a settlement, which is a big issue for new builds. This actually has, as you can see, a little cottage on it. It had a cottage on it. So we had one dwelling on 1.5 acres of land within a settlement outside of the town. And we've built 2 houses on it. So we've built one for my parents, who I think are on this call. Hi, parents. And then a new build for us. So we, after much deliberation about the existing building, decided to dismantle it rather than demolish it. So we've actually managed to reuse a lot, and I'll talk more about reuse later. But effectively, our house is a new build, and I'm focusing on that rather than my parents' house. But yeah, so this is the site. We've got a lovely slope to the southwest, and some nice views, and a few houses around us, so we're not completely isolated, which is very lovely. So thankfully this fitted the design quite well, and the next thing we started doing is digging a hole on site to see what we actually had from a resource point of view. So back in that first year, I think 2022, we dug a hole and found there is no topsoil at all, because the whole site had been just short hard cut lawn for about 50 years, maybe more. So no biodiversity, no topsoil, it's just straight to clay. And so we thought, okay, great, this is an opportunity to improve the topsoil, to build some nice healthy soil and improve the biodiversity, which is a huge part of what we're doing, but also a great resource. Clay is a really nice material to work with and to build with. So we immediately tried it out. We built actually a little tiny house, which you can see here, and then we've been living in that for 1.5 years now. Still living in it now, although we're sitting in our house at the moment. But this was the kind of trial project that we tested out the clay. We made our own clay plaster, and it's yeah, basically a retrofitted shed, but it's quite a cozy little space. And the plaster we are really happy with, so we decided we could do that in our house. And in fact, we've got a clay plastered wall behind us, if you can see our tiny little picture in the corner. But yeah, you can see it's the same colour. So then came the mission of actually getting the design detailed, and this is really where Andy will come in and talk about the detailing from a passive house point of view and thermal bridging. And yeah, I think Seb's going to talk more about the foundations as well. But effectively here you can see the amount of insulation wraps all the way around. What we've done on this site is also to prioritise, obviously, low carbon natural materials, plant-based materials as much as possible. So that means that we've lifted the house off the ground and we've used no concrete. Instead, we've got these screw pile foundations, and then everything above that effectively is timber or plant-based. And that enables it to be much lower carbon from the ground up. So we have incorporated many different materials. These are just some of them. I think there are more being added all the time, but there's lots of clay plaster. We've managed to use quite a few different materials. I'd like to try even more, and I'm hoping to try some wheat board. I've emailed them about that. So yeah, all sorts of materials, but effectively we're using plant-based hemp fibres and wood fibres, cellulose insulation, lots of reclaimed materials and home, so I wouldn't say homemade because it's clay, you know, make it, but it's there, it's from the garden, literally a few feet away. And I would like to talk more about reclaimed materials and reuse, but I think otherwise I'll be talking for about 2 hours, so I'm going to skip over that bit. But I'll just run through the actual build-ups that we've got. So, as I say, these screw piles, and then we have a glulam ring beam, wood fibre board, insulation on the underside of the floor, timber eye joists with the void filled with cellulose insulation, timbers around the perimeter. You can see the join around the glulam was done in such a way to sort of separate and minimize the thermal bridge, and then through to the internal floorboards. Obviously, with the timber floor, you need ventilation underneath, so this is off the ground, and there's a ventilated space, minimum 150 mil, or at least there will be when we finished. And the walls are made very similarly, with and this is where, when we were at Future Build, I showed the actual sample panel, which I have sitting here because we've got like a mock-up of our wall. But effectively, we've got two studs creating the frame. There's an inner stud, which is 140 mils, and an outer stud of 63, I think. And though that creates the separated frame, which minimizes thermal bridging. Thermal bridging, I can't really explain too quickly, but effectively it's the passage of heat transfer from one side to the other. So that's what we're trying to separate as much as possible and have continuous layers. So there's continuous cellulose going through all these gaps in between the two frames, and there's also this continuous wood fibre board insulation. The cellulose, I think, is 320, something like that. The walls and the floors and the roof are 300 mil, and then the wood fibre board insulation is 80 mil on the walls and 100 mil on the roof and the floor. We didn't actually end up insulating the service cavity, but that's because we just did such a good job of everything else. We didn't need to. This is quite a nice detailed showing the eaves, and again, thermal bridge free. So we've got this continuous layer of the wood fibre board, and the instead of extending the rafters out to pick up the overhanging roof at the eaves, we've got effectively the battens run down the roof and thicken as they get to the ends, so that they're strong enough to effectively become secondary rafters, which kick out slightly and create a lovely overhang. We've also, you might notice, got no membranes in our build, no breather membranes, and that's for that effectively, I mean, it's minimalized plastic, but it's also to enable the roof space to be a bat-friendly roof space. So we have and the insect mesh is also set back to the end of this this angled sprocket here, which means that there's about a third of the roof is given over as a bat-friendly space, and birds as well. So now I'm going to run through quite quickly because of time, but I'm going to run through the photos of construction. So this is when we actually began, and that was January 2024. And there was a lot of clay, a lot of clay. It rained for about 4 months solid, so we had so much mud and clay on site. They had at this point, I think, put a little, I know they hadn't put the stone down. This was the old driveway, that's what it was. It's changed so much. But yeah, so that was January. Meanwhile, whilst the groundworks were going on, the panels were being made off-site. So this is the sort of workshop where the builders were doing. You can see 2 of the panels in the background here that have been put together and ready to transport. Then I think it was about March, February that, yeah, I think it was March that the screw piles went in. and Seb will talk a bit more about the screw piles, so I'll skip over that. Yeah, okay. But you can see the piles here, and this is obviously now they've got the stone in as well. But you can see these tiny little dots. So I think there's 20 something screw piles on our house, and lots of clay. I think I would have felt a bit worse about digging so much if we had really healthy topsoil that we were then like exposing and killing by digging, because it's not actually that great to dig too much. But given that we had no topsoil, it was an opportunity to do the groundwork and now build it up. So yeah, this is when the glulam ring beam went in, sitting on the screw piles. And there you can see it sitting there on the mud. And somebody had the fun job of climbing underneath and fixing the wood fibre board to the underside. And you might notice that the floor joists and the wood fibre board layer is actually all sitting on top of the glulam ring beam rather than within the same plane. If it was in the same plane, you would need joist hangers effectively, and we wanted to minimize joist hangers as much as possible. So that was a reason, but it also made it much quicker on site to build because it was sitting things on top. And there you can see the wood fibre board. And then on top of the floor joists, once they'd gone in, we had the airtight sheathing board. So this is effectively, instead of a membrane, this is an airtight membrane. This is using a board which is creating an airtight layer whilst also providing the racking strength which is required for the panels and the floor. So this is pro-passive and it's taped to all the joints, and you can see they're also cleaning it whilst they're taping it, which is important to get the tape to have a good stick. Then very quickly the panels arrived for the walls and up they went in no time at all. We had a ground floor and it was yeah, really exciting, big moment. It kept raining, so it got wet on site, and initially I was very worried, but actually it was it all dried out and I was reassured, and it's not been a problem. Yeah, you can see them putting, and then this is then the first floor, and they're putting the first floor panels up. It's all, they're sized so that they can be manhandled into place rather than needing a crane. So that was another pro about this approach. Obviously, going for prefab panels means it's a lot quicker to build, but yeah, it was one of the options we were looking at is a type of panel that didn't need a crane to come onto site because of our site access. And this is just a close-up showing the C16 grading of all the timber. So it's not C24, C16, which means it can be UK. Are you going to talk about that? Right. No. Yeah, so C16 means that you can basically use British timber, and we have loads of lower grade timber in this country, but engineers like to spec high grade timber, and that often means you have to go abroad to get it. So it was really nice to be able to do almost the entire house using C16, which enables that locally sourced timber. And there we are sitting on a beam not having lunch, but that was an exciting moment. That was one of the beams that is sort of like the tie beam going across the truss for the roof. Then the roof went up very quickly, the ridge beam, the rafters. We had a little topping out ceremony. You can see my little tuft of tree there stapled to the top of the apex, and then the wood fibre board went on, and that instantly gave us obviously rain cover, and it then sat there exposed to the rain. Wood fibre board does amazingly well at this. It's something that you might think is very susceptible to water damage, but actually it can be left out for a very long time in the rain, like months, and it's been absolutely fine. Then we had some slates. I really enjoyed finding some nice reclaimed slates. And just for comparison, you can see my parents' house in the background there with its new Spanish slates compared to our far superior. And reclaimed Welsh slates, which came from apparently from a castle in Wales. I need to find out which one. It's very exciting. They're huge, heavy, and they're sort of all slightly different. And I insisted that they put them not perfectly, because I like things to be textured and imperfect and handmade, rather than looking like it's all too flat and machine made. There's Seb putting some moisture meters in. He's going to talk more about. And then the windows arrived. So we're now into the summer. Well into the summer, actually. It was, yeah, August or September even, I can't remember. And yeah, windows and doors all went in. These are all triple glazed timber windows and doors from 21 degrees. And there weren't a lot of options with this, because I was looking for a timber window and door, not a composite material, and not with aluminium on the outside, just timber really. So yeah, not as many options out there, because a lot of the high performance windows actually are more composite, but these are made of Accoya timber, which is very stable. But that means it's engineered timber, so we went for a painted blue colour, just because it doesn't look, if you leave it natural, doesn't look as you would think a sort of a timber window would look. You can see the kind of finger joints and things. So we decided that actually painting it was the best thing. So yeah. That's then, you can see the eaves, so from that sketch to reality. And there's a tiny little bit of membrane which was used to just connect the wall panels of the top to the so like the first floor to the ground floor walls, because the floor itself, the intermediate floor, was sitting on the ground floor panels, so the first floor had to sort of have a little wrap around just to join those two for an airtight, because it needed to be a continuous airtight layer, and that's a really key principle. Meanwhile, we were seeding up lots of lovely wildflowers and growing things, and you know, we've been, as I said, building up the soil is important to us. We're also doing a lot in the garden with vegetables and things like that as well, planted an orchard and things. Meanwhile, yeah, this was then I can't remember when, in the summer, late this, we're now into autumn, I think, aren't we, when the render finally arrived and went up. So we've used lime, and you'll see that lovely rounded corner there. That was hacking away at the corners because I didn't like sharp edges. Normally you would have a sharp edge and a plastic beading to strengthen the corner, but I just sort of went at it with a knife and took the corner off, which of course means that you don't need the plastic beading. So that was a nice little win for that. And then the render goes on in 2 coats with base coats, and then it's with a scratch in it, and then the top coat goes on as well, which we went for a pigmented top coat so that we don't have painted render. This is pigmented, and it's also done very roughly on our instruction, rather than as they wanted to do it perfectly smooth and flat. We wanted it a little bit more rough and ready, which I really like, and I think it looks much more characterful and rich. So that was it, looking rather lovely then. And then I think, well, this was getting up to Christmas when we got partial possession. Actually, just before that, they insulated the inside. So this is all, that's all to do with the shell. Then we come to the actual insulation, which is pumped in to all the voids after the shell is complete. So they do this from the inside by drilling a hole and putting the cellulose machine in, pumping it full, and then slowly pulling the nozzle out when it's at the right density, right pressure, and then they tape up the hole again with this blue airtight tape. And here you can see the cellulose made from old newspaper, shredded newspaper. And then we come on to we got basically we got to take it from there. So all the insides we are doing ourselves. This is for one of the some of the internal walls we were putting light earth in, and light earth is a mixture of straw and clay slip, and you coat the straw very lightly in clay slip, and then and we were doing this in the inside the internal walls for acoustic insulation, but also thermal, and also a plaster carrying surface, and it costs next to nothing. So yeah, it takes a bit of labor and a bit of time to dry, but I'm really happy with the result personally. I think it's been really lovely to work with. We did actually find that because on this section we had a structural bit of OSB on the back of this stud wall that stayed in place rather than being temporary shuttering like the pieces on the front here. It did struggle to dry out through the back, and we were monitoring that. Seb's going to talk about that. Oh, I was jumping in. No, okay. So I'm going to move on to another thing we tried is using lath, and this was homemade lath. This is a picture of Tab doing it because she came to volunteer, and we actually ended up stapling it. But this is what we get from a building site, even the good ones. There's a lot of waste, a lot of offcuts, and yeah, it's very frustrating. I hate waste, so I've been much to my parents' dismay, having piles of scrap material everywhere. But this is a really valuable resource as far as I'm concerned, because we've been ripping this up into lath and stapling it onto the walls and then plastering onto it, which has worked really well. We've also been using reed matting, which goes on. So this we were stapling straight onto the OSB board, the sheathing board on some of the internal walls, and then again plastering onto that, and that worked really well. So yeah, mixing up the plaster, we've got clay, lots of clay, plenty of that. We very simply mixed it with water, it made it into a nice thick clay slip, poured it through a sieve to get the bits out, and then let it settle a little bit to get the right consistency, and then mixed it with fibre and we had the fibre as well, because we've been using the waste from the wood fibre board. I haven't got a picture of that, but the wood fibre board that we've been using as insulation, every time you cut it, it creates this kind of very fine fibrous dust, which is lovely fibre for plaster. And you can sort of see that the flecks of fibre, it's very fine, but it works really well, and I highly recommend it. So yeah, we put that onto the reed, onto the light earth as well, and onto the lath. And then yeah, so this is our kitchen. You can see there's a bit of a light earth wall here, but then the external walls we used the lath to cover, and then we've done this detail around the windows as well with using scraps. So this is wood wallboard, so that's waste. It was dug out of the skip, but that is perfectly good for creating sort of small patches around the windows and doors. And then you can see the lath all over the walls, and then we've sort of given them a quick brush with clay slip just before plastering, because that helps with keying. But yeah, we've had loads of volunteers come and help with this, and it's been really good fun. And that's it plastered, which is looking lovely. Yeah, and then skip forward to a photo I took yesterday, and we've actually now painted the walls. We've got ceiling plastered, and we've put a bit more of a camp kitchen in for all our volunteers who keep coming and helping out. So shout out to anyone who wants to come and volunteer, please do. We've got a lot more to do still, so we would appreciate more help. Yeah, it's been a really nice journey, and it feels so nice in the house. It feels so comfortable, and everyone comments on how it's sort of it just feels good. It feels, the smell is right, and it's something about it. The atmosphere is really lovely. So yeah, come and have a play with some clay with us. That is it. I'm going to pass on now, I think, to Seb. I'll just switch over. Hang on. Shall I? I'll just start sharing again with Seb's.
Brilliant. Yeah, thanks. Good evening, everyone. It's really nice to be back on an ACAN call. Janna and I were reminiscing. This is basically how we spent our lockdown.
Yeah.
Rushing from work, cooking some dinner, and then spending an evening on Zoom with some other people who were too frustrated at the inaction in the industry. Yeah. I was doing the embodied carbon group and Janna was doing the natural material group, and we were like on separate calls. It was hilarious. So it's really nice to get to be presenting back to the community and seeing that it's still thriving. Yeah, absolutely. So I'm Seb Lomas. I'm an associate at Architects, 3 studios in Hereford, London and Edinburgh. And I'm going to talk a little bit about the screw piles that Janna mentioned, and then also moisture management. So starting off on the ground screws, this is something that I'm really glad we were able to get to do. When we were at university, screw piles were seen as kind of like the cool, great way of avoiding the huge environmental cost of foundations. And all the projects I drew had screw piles. And then when you're in the commercial world, it's very rare that you get an opportunity to actually use screw piles. And so it was really nice when we were kind of developing this project, which was Janna didn't mention, but she designed it to be materially agnostic from a system perspective, so that we could go to different contractors and be like, okay, straw bale contractor, how would you do this? Okay, timber contractor, how would you do this? And kind of leave our options open, knowing that we've got enough of a wall zone for whatever system is then deemed the best for the site. And then it so worked out that the screw piles worked with the timber system that we were using, which was brilliant. So this is the detail that Janna talked through earlier. They protrude 150 mil above finished ground level, and then you've got the glulam beams with then that very well ventilated undercroft that runs underneath the building. And from an embodied carbon perspective, we didn't do a life cycle analysis through the design process of the house, and we didn't feel we needed to, because we inherently were doing what we thought and knew to be the best options at any one point in time. And I will happily put my hand up and say that, sure, some things could have been lower, but one thing, so we're now looking at doing an LCA of the project using the bill of quantities, so it will be a highly accurate count. But I did do this EPD comparison as if we had an RC strip foundation versus the ground screws. And so you can see if it had been a traditional RC strip foundation, which it could easily have been if it were being built anywhere else, that would have been 7 tons of carbon emitted there and then, which is the equivalent of basically like one person's carbon footprint for a year in England. And we were able to bring that down to under 2 through using the screw piles. And very positively, screw piles are inherently circular in their opportunities. There was a building in London, in Chelsea, which in the 1900s, steel sheet piling went in the 1910s. And in 2000, they pulled it out of the ground because they were doing works, and they were able to reuse the same sheet piling elsewhere that year. Which I think is an amazing demonstration that, one, yes, it can last a really long time, and two, it definitely can be circular. And Janna was telling me that the subcontractor who does this actually used them multiple times on temporary buildings. So, I mean, it's a brilliant thing and quite interestingly, so they can be sized specifically to the loading requirement of the building. They come in all shapes and sizes and have a 125-year service life. but there's no reason why they shouldn't and won't last significantly longer than that. And they go in the ground with basically a massive screwdriver, which it's an amazingly low tech and fast and cheap solution. And quite interestingly, the contractor we were working with for this project had never used screw piles before. And having done so, they said it was cheaper, easier, faster, and more enjoyable than a concrete foundation. They've basically said they want to adopt it as a system, and they're now licensed as a kind of stop digging installer, and have kind of already looked to swap concrete schemes of theirs to screw piles, which is, you know, absolutely fantastic. That said, we have I've spoken to other people about doing screw piles, and some quotes that people have been receiving are, you know, extremely high. I think it was £8,000 for the 2 homes for the screw piles. And I've had friends with garden rooms in London being charged over £20,000, you know, for 10 screw piles. So
you have to look around a bit.
Yeah, absolutely. But so this is them going in. So on the left hand side, you've got the chap with his big screwdriver, and then the diagonal pole is a kind of it resists the torque of the driver, and it keeps things in alignment as they're going down with a spirit level. And then on the right hand side, you can see what they're doing is that it's a load cell, and they put in 2 piles, they put a beam across, and they put this load cell in the middle, and they're looking for how much it deflects when they put it under load, and they use that to then optimize the specification of the screw piles for the scheme. And we were actually able to down spec the screws because of the very high loading capacity of our clay. And then, as Janna said, you know, the glue lambering beam very, very accurately sits on top of this. Similarly, I've heard people have really bad experiences with putting in screw piles and finding it hard to make them accurate. And it wasn't our experience at all. And it was really enjoyable to see how precisely everything went together. So the other thing I'm going to talk about is moisture monitoring. And I don't know if people will be familiar with this, but there was a recent payout of over £100 million for a Sky building, which had a mass timber roof that was suffered from water ingress and then was basically condemned. And that single payout means that there are now more losses from water damage than fire damage as an insurance model, which basically means that when you speak to an insurer now, the primary concern is not fire, it's water. And it's quite interesting because for the last couple of years post Grenfell, there's been a lot of energy in the industry about addressing the fire concerns. And there's been a fraction of that focused on water. And there's a lot less guidance out there. I've put the mass timber insurance playbook up there because it does have some information in there about water. But there's a big gap in the industry when it comes to sufficient guidance for designers taking it through a design scheme and kind of courting the insurance market, as people put it. But positively, there are some insurance providers who are very keen on the idea of using data to drive insurance profiles. And I know an insurer who basically says, well, if you show me the data that your building is dry for a year, I'll give you a lower insurance premium, which I think is really exciting. And also builders are quite keen to have the data on their buildings, because then they can then tender for the next job and say, like, look, we've delivered dry timber buildings and here's the data to back it up. So people are quite keen on the idea of getting this data. And Janna and I were really keen to kind of learn from the building process through kind of trialing it and learn more about it ourselves so we can advocate it for projects and clients.
And provide it for others as well.
Yeah. Exactly. So we went to Tector, who were called WoodSense at the time. They've got what I think to be a very competitive offering. The sensor, each sensor is about £150, and then there's like a gateway, uses low frequency Wi-Fi network, which is £300, and then there's a subscription model for kind of accessing the data on the platform, which is really, really decent. The sensors have got a 10-year battery life. So the idea is you build them into the building as you go, and recording them as you install them. And then for 10 years, you'll have that operational data. And of course, something could go wrong in year 11. but at least you've got that certainty for the first 10 and the anticipation that things will continue in such direction. The website basically then just live draws all the data. You can like automate reports if you were like an asset manager or responsible for the building or going for your insurance premium. And yeah, there are other platforms out there. This is just the one that we used. So as you're building the building, you pick where you want to put your sensors. There's no industry guidance about how many or where. It's kind of, so we did it from what we wanted to learn from the building perspective. You take photographs as you install them, so you've got that record, and then you tag it with all of the metadata, like what have you screwed into, what type of wood is it insulated, uninsulated, and then basically that it's recording humidity and temperature around the sensor, and then it's recording the moisture content between the two screws that go into the wood to fix it. And if you wanted to, you can install them in the factory and then actually collect the data as it's going from the factory onto site through the assembly process. So you've got the whole moisture journey of the building, which I think is really interesting, especially when you're talking about mass timber, which is harder to dry out. Fortunately, the section sizes on this house are very small. So even if the timber did get very wet, it did dry out relatively quickly. So we kind of decided what we wanted to learn from the building. So we've put a number on the southwest wall all the way through the build-up. So we've got the moisture journey through the wall. We've got 2 in the floor, 2 in the roof. And then we've got 1 which we had in this internal light earth wall that Janna mentioned about. And it was really interesting that we did that because it is what highlighted that it wasn't drying out against this OSB. And then, so we intervened, we drilled some holes, and, and it's dried out nice and quickly now. But we learned that lesson. On the roof, Janna said that we wanted to have a kind of like bat-friendly roof. So we've got no insect membrane, and we've got these reclaimed roof tiles, and then it's basically battened straight onto the wood fibre board. So again, we were quite keen to be able to demonstrate that works from a moisture perspective and from a resilience perspective. So what you can see here is on the top, you've got the moisture content of the timber frame in the insulated zone, and the temperature on the bottom graph. And it shows the precipitation in the local area at that point in time. And you can see that there's no impact whatsoever on the moisture content in the roof, even though we had, a really, really heavy rain spell, which is just really positive to be able to communicate.
Just say that should be breather membrane rather than the insect membrane, because we have an insect mesh on parts of it, but not, it's the breather membrane is usually the rain barrier.
Yeah.
Sorry.
No, it's a good point. Live critique as we
I
go. I love it.
Sorry.
So then we've got 2 in the floor, and the data here has been quite basically it's just showing that the frame was slightly wet when the insulation went in, and then the wicking element kind of dried it out very quickly, and then since then nothing exciting has happened in the floor. And then this is the external wall. It's showing some interesting things here. So the dark blue is the timber on the outside face of the Larsen truss, and the red is the timber on the inner face of the Larsen truss. And you can see that the outer timber is being really affected on a diurnal basis by moisture content and temperature, whereas the red line, the inner one, is completely unaffected by all of this activity that's happening on the outside. So we can see here that the timber on the outside of the building is absorbing and desorbing moisture on a daily basis in response to the temperature of the outside environment, but very positively, the inner timber frame is completely unaffected by that. So we've got that whole breathable buildup that's kind of allowing that activity to happen without it having any kind of like long-term impact on the stability of the house, and also showing that thermally as well, it's very unaffected by the ambient temperature, even though we're not even heating the house yet.
What's the light blue one?
The light blue, so the light blue line here is the service cavity, which is on the inner face into the kitchen. And basically it got very wet because we were plastering, which is what you can see on the left-hand side of the graph. And then as the plaster then dried out, the moisture content in that timber then came back down to below 20. And then this is the spine wall that Janna mentioned that we did the light earth on. And you can see that the timber before the light earth went in was at 15%, super dry. And then by the time we finished all the light earthing, it was, it was almost up actually at 30%. And then, so we intervened and it's now brought it back down. But really useful to be informed by, the monitoring. And lastly, this is kind of like the big event that happened. So the wood fibre was being applied to the outside of the Larsen Truss wall, on a program basis because it was critical path. And just as they were getting to putting on the wood fibre board, there was an extremely wet weather window, and the whole frame got very, very saturated. But the wood fibre board went on. We were being told by everyone that it would be okay and it would dry out. But we had the moisture sensors already installed, so we were able to show exactly that happening. So it got over 60% from moisture content, which is really not in a good place for timber to be at for a prolonged period of time. But then the warm cell was installed. It was became a dry space, and then you can see that the timber desorbing back down to a very stable level, which is now completely unaffected by external rain events. So yeah, an interesting, really interesting platform to mess around with. And yeah, thank you very much.
And we're handing over to Andy now from Grain Architecture.
Thanks, Janna and Seb. Andy's just getting his slides up.
1 second. Okay. Hi, I'm Andy. I'm one of the directors at Grain Architecture along Janna. I'm also a certified passive house designer. I trained on the what was then the ACB warm passive house course. And I'm the the delivery architect on this project. So this goes back to some of the things that Tab was talking about at the start of the project, which is the criteria for what defines a passive house. Because to design a passive house, you basically need to enter all the information about the building into a very large spreadsheet called PHPP, which is the main tool that's used to model the behavior of the building with weather data, local weather data for the building site. So you have to enter in all the areas of all the walls and windows and doors and how deep the reveals are and everything. And basically that generates some key numbers, which are the numbers you need to achieve. The key criteria, some of the key criteria are the heating demand. So you need to have a very low amount of heat required to heat each square meter of the building, or an equivalent sort of maximum heating load for the year. A very strict air tightness requirement of less than 0.6 air changes per hour. And the requirement to be have minimal thermal bridges or virtually thermal bridge free, and I'll talk about how that's possible with the way Passive House does the calculations later. And for the ventilation system, there's a requirement for a mechanical ventilation system with heat recovery, which can recover at least 75% of the heat that would otherwise be lost during the heating period, so in winter essentially. So that guarantees you've still got fresh air all through the year without losing the heat that you would otherwise be losing. And there's also a primary energy renewable target, which deals with the in-use carbon essentially from the heating system and renewables. But we're particularly going to that. The table on the right is the heat balance table, which is one of the key sort of charts displaying the data that comes out of Passive House. So all the information in the spreadsheet generates this table, which is looking at the heat losses on the left against the heat gains on the right, and those two charts have to be balanced. So to make up the difference in them, you have to add the heating on top, and that heating you can see the number 13 on it. So that's the heating demand that we're needing to meet less than 15 kilowatt hours per meter squared per year, and we're currently at that's showing it at 13, so that's us meeting it. There's a slight difference in the height because we've got actually overall negative thermal bridges, so that's taking it off the top of the losses. So I came into the became involved in the project at planning stage, and as Janna said, she's been designing this house for a very long time. So it wasn't a matter of me designing the house so much as helping optimize the design to achieve Passivhaus. It was starting from a reasonably compact and efficient building with larger windows to the south and small windows to the north. So it's a sort of a fairly good starting point. So what I did was enter in all the information as it was designed into Passivhaus, and then look at where some improvements could be made. So it was looking at adjustments to the windows, losing a few of the windows that were particularly bad in terms of losses, and sort of just optimizing them a little bit so the northeast windows became a bit smaller in particular. And the other thing that had been built into the design was significant overhangs, particularly on the southwest, which means that we get, particularly on the south windows, we're getting significantly more gains in winter than we are losses. And that is done without overheating in summer by the deep overhangs, and we'll have, when it's built, we'll have shading to the ground floor windows with a glazed veranda, glazed pergola as well. So you can see on the chart on the left that the windows to the south in winter are gaining more energy, more heat than they're losing, whereas the windows to the north and east are actually losing slightly more. So that's where you want to optimize, by having enough light and having nice bright spaces, but without having too much heat loss. The other big thing in terms of having an efficient building in PHP and more generally is having an efficient form for the building. And in Passivhaus, that's considered in terms of form factor, which is the heat loss area. So that's the external fabric of the building that's losing heat, divided by the treated floor area, which is the measurement that Passivhaus uses for floor area, which is slightly more accurate and detailed to calculate than standard UK measurements, as the Germans like to do things more accurately quite often. And so you can actually see visually on the left for each of the floors what that area is. So basically, for most spaces, it's that are more than 2 meters in headroom. It's just the internal rooms. It's the full area. In then spaces where you're less than 2 meters, you include that area at 50%, and then below 1 meter, you don't get to include that at all. So it's sort of basically a measure of useful floor area. So what you're looking at is trying to maximize, in terms of pure efficiency, you're looking at trying to maximize the useful floor area for the amount of external surface area which is losing heat. Some of the features design meant this wasn't sort of as optimal as it could be, but were done for aesthetic and spatial and design purposes. Were the having a large open stairwell to create a really nice feeling of space over the entrance, and the room in the roof reduces the headroom on the second floor, so that reduces the area. But that was restricted partly by planning restrictions on the height. That's partly why we're having to bury the house down, and also the design of not making too large a building. So there's compromises with it, but overall it's still coming out pretty efficient at form factor of 3, which is about where you want to be for a detached house. It's about 3 or better to achieve Passivhaus. So the key thing with Passivhaus in terms of the fabric of the building, the walls, floor, and the roof, is to get as Tab mentioned, a high level of insulation, which is continuous around the entire building. And that was achieved by essentially having the same system all the way around the building, or very slight differences. So as Janna said, we have screw piles supporting glulam ground beams with timber I-joist floors, filled with warm cell recycled newspaper insulation, rigid wood fibre underneath, and then flooring, airtight board on top. And that essentially is the same way the walls are built, except the walls were done prefab as the panels, as Janna showed. And one advantage of that is you get very high tolerances in terms of the design, going to a couple of millimeters in the design, because it's all done in a warehouse with relatively simple tools actually, but just to quite high levels of control compared to site construction. So ideally for passive house targeting, your building system wants to be able to achieve a view value of around 0.1. And that's around where, I can't remember the exact values, but they average around 0.1 on the project. And as Janna mentioned, the repeating thermal bridges from the I-joist in the floor and roof and the space studs in the walls mean that there's relatively little continuous timber all the way through the walls and floor and roof. And also with the rigid wood fibre wrapping the entire way round, it's got a pretty good continuous layer of insulation between the warm cell and the rigid wood fibre. So on the right there, you can see that's the warm cell. It comes in these big bales, which get blown into all of the voids. And then it gets wrapped with rigid wood fibre, and that's fixed with these little washers to hold it in place. And they've actually got recessed screws, because in Passive House, technically even in SAP, but often I believe people don't, you have to include every fixing that goes through the insulation layer. So to reduce the impact of those fixings, the screws are recessed into the wood fibre, and there's actually a little insulating cap that plugs that. And on the right there, you can see that some of those have got these little white caps, and then that one's not been fitted yet. So you pop in these little things. It's quite a satisfying process. But yeah, that just means that it gives you you reduce the depth that the metal is going through the insulation. So on the inside of all those elements, the wall, the roof, and the floor, we have the airtight board. I think they've renamed it now to I think it's called airtight board or something. It was pro-passive when we were doing it. So that creates a continuous layer all down the inside. And then all the junctions, penetrations, and surface penetrations, and any screw holes that go through it, that needs sealing with either airtight tape or airtight paint. So that's the blue patches, the blue lines, which are all the junctions with the windows and everything, and some of the screw holes. Then got some airtight paint, which that purple bits you can see. And then on the inside of that, we have a services cavity, which 45mm deep on the walls, because we'd originally it probably doesn't need quite as deep as that, although it was quite useful for getting more things in there. But that was because we were allowing for the potential to increase the insulation slightly more inside of the airtight layer. In the end, once we got our airtightness test, we didn't actually need to have quite as much insulation, because it was so airtight that it was more airtight than you have to allow by default, I'll phrase it that way, in Passive House. So that airtight layer, you should be able to draw a continuous line around the entire building. So that's on the inside layer. Ideally, that should be as simple as possible for construction purposes. You can see there's a few areas where it's a bit more complicated. So at the internal floor joins, where the wall panel and the lean-to are, so it's not a simple thing. It's got to wrap around that panel because it's a panelized system, and also over the trusses in the roof. There's a few areas where it wasn't quite as simple to get the airtightness to work. So those were the areas we had to use a little bit of airtight membrane, and it was essentially a matter of these will. It's a lot easier to deal with these sorts of issues if they're thought about in advance. So before any structure was put on top of the truss, and in fact before it was even inserted into the walls, it was wrapped with airtight membrane with all the joints sealed and taped so that they could then be taped to the airtight layers as they came in. And similarly in the walls, in where the internal floors meet the external walls, because the ground floor walls were built first, then the first floor is built off the inner stud, but it's already wrapped with membrane. So you can see that white membrane there. And then a little external wall was built to build up the difference. And then the next floor is built up from that layer, sitting on top of that already wrapped airtight layer. So it's slightly awkward, but if it's planned for in advance, then it can be quite a neat detail. And then where the lean-to comes in, that membrane wraps all the way down round that whole panel, and then that's boarded and taped to the airtight board afterwards. There was one particular point which wasn't picked up, which was essentially something that wasn't planned for, which was that the way the contractors had always been building, they had their internal walls interleaving with the header and binder of the internal walls interleaving with the inner leaf of the external walls. So you can see that that top timber is actually going through the airtight layer, which it wasn't necessary structurally, it was just their standard detail. So that was something that had to be dealt with on site. It had to be cut back, the junction taped and sealed up. So that's something that it was an error, it's picked up, and it's something we won't do again because we know this is something they might do. And it's a lot fiddlier to do that sort of thing if you don't think about it in advance, but at least it was picked up and fixed. So when you've got all your airtight layer complete, including all the windows, with any low energy building, it's always good practice, and Passivhaus is essentially a requirement to do at least one additional air test. You've always got to do an air test at the end of a new building to get building control approval, but to know that you're on the right track, it's much better to do an airtightness test when the airtightness layer is still accessible, so that any errors in it can be fixed at that point. So the Passivhaus airtightness test standard is slightly more rigorous than the one for building control, in that you have to do a depressurization and a pressurization test to make sure, because if you just blow it one way, pull the air in one way, you can actually be pulling membranes tight. So by doing both directions and taking the average, that gets you a much more accurate airtightness figure. So we did that when we got all the areas sealed, and that's the blower door which sucks air through, and got a figure of 0.28 when the Passivhaus standard is 0.6. So we're slightly better than twice as good as the Passivhaus standard for airtightness, which is great. There were a few things we didn't quite get straight to that level immediately. There was a few issues that were picked up, and one very useful thing when doing the airtightness test is to have a thermal camera, because you can more visually see the movement of air, particularly, and which is this is easier to see when you've got the pressure forcing the air at pressure through the building, so you can see the air moving towards any weaknesses in the building. And there were a few little things. It was picked up that some of the windows and doors needed more adjustment, and that's something that will actually improve the airtightness test when it's done for the final test. And there was also actually one of these little plugs where the cellulose insulation was blown in, that wasn't taped up properly. So we had a little hole that was actually a significant loss that might not have actually been picked up if we hadn't got the thermal camera when we were doing the air test. So one of the other key requirements for having a very efficient building is to have sort of a thermal bridge free, or certainly very minimal thermal bridge in bridges for the overall building. The reason that in Passivhaus you can say thermal bridge free, because a thermal bridge is just any point where any material that is any conductive material that is going through the insulating layer, so it's basically a weak point in your insulation, and you also have any junctions, external junctions, also essentially act as thermal bridges. The reason that in Passivhaus you can achieve a thermally bridge-free building is because you actually measure the external dimensions of the building rather than the internal dimensions. So, which is in SAP and built for building regs, you use the internal dimensions, which means that the external corners on any external junction, you have that area that's not counted. In Passivhaus, you double count that corner instead. So that means that if you actually then go away and calculate the real heat loss through that junction, it might actually be less than you've already allowed for just in your U value calculations. So that's why you can actually end up with negative thermal bridges. If you have a continuous layer of at least 2/3 of insulation all the way around the building, which is what you should be aiming for ideally with Passivhaus, then you don't necessarily need to be calculating all the thermal bridges. But there's a few areas where we couldn't avoid thermal bridges, particularly with the things like the screw pile, where the glulam ground beams are. the structure from the walls carries on through the floor, so it's not as thick wide as the ground beam, but there's still a significant bit of timber taking that load down, which is a layer where it's essentially continuous timber from the inside to the outside. So that's the thermal bridge that needed calculating. However, because timber is relatively non-conductive compared to something like steel as a structure, even though we had this continuous bit of timber going from inside to outside, the overall depth of the insulation and the relative lack of conductivity from timber means that it still actually comes out to overall a negative thermal bridge on the wall floor joins. Where the internal walls land on a glulam beam, that is actually a positive one, so they did still need calculating, but by doing this you can actually then sort of get a much more accurate picture of what's happening at all these junctions, which it's useful from as an architect learning to the process of calculating thermal bridges. It sort of teaches a lot about the way the heat actually flows through junctions, because it's not as intuitive as you might think. But overall, on average, when I did calculate all the thermal bridges, we ended up actually overall with negative compared to what the measurements for U values ended up giving us. One particularly neat area that Janna had mentioned, which for producing thermal bridges, was the detail we came up with for the eaves, which was this splayed batten that Janna's talked about. It had to be 2/3 the length fully supported to enable it to act as a cantilever. But it did enable us to have this quite neat detail where the only fixings for the eaves are the same fixings as the standard battens fixings throughout the rest of the roof, which enables essentially no extra thermal bridge at the eaves, especially when the cellulose insulation carries on wrapping round through that junction. Yeah, it ends up with very minimal bridging here. And that's the calculation actually showing it, which again comes out slightly negative compared to the calculations just looking at the areas. And then you can actually see that how it's constructed. This is at the where the external wall joins, but you can see those eye joists, and they're just landing against a ply board, which is that board there. So that's the only sort of big bit of timber in that area. So you've got very continuous insulation, and then on top of that you've got the rigid wood fibre wraparound as well. So that's sort of the main aim of these sort of junctions, to have as much continuous insulation as possible. And there you can see that then the splayed batten in reality, which also does kicks up the eaves, which is quite common in traditional buildings as well. The requirement for the MVHR system to be minimum 75% ventilation system, which covers 75% of the heat. Because of the aims to minimize embodied carbon on the project, we were looking at we're using timber eye joists for the internal floors as opposed to web joists, which are quite common on these sorts of projects. Which does mean you need to account for all of the required centers that you're allowed to make holes in the eye joists, which from our initial MVHR design, you can see they didn't actually properly account for, because they just had all these ventilation ducts running next to each other. So basically, it was a lack of understanding from the initial ventilation designer that we had from the building. So we ended up having to find another designer for the system, and actually on a recent project we have spoken to a builder who was saying that they actually preferred using eye joists because they just know the centers you can go to, and it's actually in a way slightly more flexible than the web ducts, the web joists, because you can never go through the metal bit, whereas as long as you've got the spacings correct, you can always go through the eye joists. So it's a way of reducing the metal a bit further in the project. You've just got to allow for it in the design. So instead of this system where the layout for the ventilation where it was all going through the hallway before spreading out, what we've ended up doing is splitting the ducts to go vertically, and then have ducts running down the eaves in the loft, which is good use of that sort of minimally useful space anyway. And then down, and then others running down in the along the spine wall on the ground floor. And there's the MVHI unit going in, which you see the sort of highly insulated ducts going to the outside. So one's, I can't actually remember which one's which, but one's the fresh air intake, and then one's the exhaust going outside. And because they are the ducts before and before the air has been exchanged and after it's been exchanged when it's going out, those are essentially external air. So they are thermal bridges to the outside. So you want to minimize the length of those ducts as much as possible. So you can see there it's a relatively compact and short distance from the heat recovery unit to the outside. And it's all been done and sealed very neatly. So that's how we've achieved these standards, which for the air tightness, let's say we've got 0.28, so that's twice as good as the requirement. And currently, this is slightly out of date, actually, it's updated, but from that, but yeah, we're easily meeting the overall heating target. So currently on track to be meeting the standard. Thank you. I'll stop there.
That's brilliant, Andy. Thank you. I'm just going to try and add spotlights to everybody, and I've lost Jonathan. He's disappeared now.
Promise, I'm here.
Spotlight, and I probably lost myself as well. So Jonathan very kindly is going to ask all the amazing questions you've put in the chats, and maybe some more. Now, obviously, we've already run over time, but let's aim to wrap up by 5 to 9. We have got an open invite to a pub afterwards, and it is literally an online pub, but we'll put that in the chat at the end for any of you who stay there. Jonathan, over to you.
Thank you, Tab, and thank you all to the amazing speakers and all your wonderful sketches and all the lovely comments that have come through in the chat and the insightful questions. So as it is in the title of this presentation, why did you decide to go plant-based for the construction?
Well, I'm glad you asked that one. I should have said more about it, really, because I usually harp on about the benefits of plant-based for half of a presentation. Because there are so many, I suppose. So we answered a little bit in the chat. Basically, we've got embodied carbon as a significant factor. We've also got, I mean, where to start? The kind of ethos that we build with grain architecture and just ourselves is to minimize our negative impact, and that comes through many ways of avoiding using fossil fuel based materials. So using plant-based materials was really important for that. Obviously that is highly linked to embodied carbon, but also from a resource point of view. There's also the performance of them in use, and the fact that they are breathable, non-toxic. They are much nicer to work with. They're not creating sort of off-gassing or toxins in the environment. They also, when you have waste at the end or the leftovers, most of them can be composted, which means they're nice and circular. Some of them are local. I mean, the straw is obviously the clay is, but there's a lot of reasons. There's probably more than that.
That's quite a nice one. So the farmer that Janna sourced the straw from had no idea that straw could go into buildings, and I thought that was quite an interesting indictment of how far we've got as a society. Like we've moved that far away from how most of our homes used to be built, and the same thing with cob or clay and earth. As Janna said, there are lots of reasons, and it's been really nice with all the volunteers that have come and helped out with, and we're really grateful to every single one of them. They've said how nice it is to work with, because with every other building material, you don't want to get it on your hands, and you want to have a respirator on, and you've got to wash everything afterwards, and everyone's just like, delighted to go straight from like having clay on their hands to
I mean,
having
it gets
lunch.
smeared on faces
Yeah,
quite quickly.
yeah, exactly.
Yeah.
And just everyone remarks at how nice it is that those are the materials that you work with, you know, for your day.
Yeah.
And
yeah.
there's another really nice thing that Janna's talked about is like people say like, what do you want your building to be like in 1,000 years? Like either really, really well loved and well used still,
And still going,
or completely just biodegraded into the ground with no sign of it.
Yeah, exactly. You don't want it halfway. I mean, a building to last as long as it can, and still perform and still be usable as long as it can. But ultimately, nothing is permanent, and we want it to completely be returned to the earth and be, recycled or composted and be circular. We don't want to leave a trace, and so yeah, it was a big criteria to try and do as much with compostable materials. And I think there have been a few things that I would, in hindsight, do differently in that respect. So, for example, the airtight layer, I think actually Tom Graham has used the paper-based airtight membrane on his house, and I am slightly envious of that now, because I feel that would have perhaps been a better product from a natural material perspective. But I mean, we've done pretty well, so I'm not going to beat myself up about it. But I do think that, you know, there is a lot of waste and things like the propylene and the tape, everything that's going into the skip and the end of its life. I'm really, really, I guess I really kind of feel the where it's going to go really bothers me. Like, what's going to happen to that? Is it going to be burnt and released into the atmosphere? Is it going to end up in landfill, breaking down and turning into microplastics in the soil? And the answer is probably one of those for some of these plastic materials, like the pro-passive boards, the airtight boards. There is no end of life strategy for it yet, so that's a bit gutting to have to use some materials like that. And as somebody's in the chat said about the sort of what was it, the vitamins of the building, you know, they're small amounts that we're using these high energy materials or non compostable materials for. The vast majority is natural, but yeah, there is a small amount that is needed.
There's another one about like through using something that you know that can break down and be more kind to the planet and its end of life scenarios, you're also avoiding future liabilities and future issues. So when we were taking apart the cottage that was on site, it was a brick cavity construction that had been insulated with blown polystyrene beads. And when the builder was taking apart the building, these beads just started being blown everywhere. You know, we had chickens, and the chickens were pecking at them, thinking it was food. It was heartbreaking. And the bees were going everywhere, and they'd been told by other building control authorities
I think it was the Environment Agency.
That's a contaminated waste, and it needs to be flushed down the loop, down the drain, all the polystyrene beads,
because then in theory it ends up in the water system, which is filtered, and then they can be taken out. Whereas if they go into landfill, obviously they'll end up all over the place. I mean, it's neither are good.
No.
But yeah,
there's
a lot of this to deal with in the industry.
Just not thinking about the implications of the thing that you put in a building now.
Yeah, because it's not going to last forever. So what happens at the end? I mean, now we are going to be making bean bags for everyone.
We got 4-ton bags filled with polystyrene beads ready to go to bean bag.
I think it's worth just commenting on how he got the beads, because they used the machine that they used to install the warm cell insulation as a giant hoover to suck out as much as they could. So that was even the stuff going everywhere was even with them trying to get as much as possible to stop it going everywhere.
We were down on the ground, like picking out every single bit. So, I mean, we probably didn't get every bit, but yeah.
It's going to be your garden, isn't it? You don't want it full of polystyrene. But it's a wonderful holistic view of these things, which otherwise are far too often just completely, if you'll pardon the pun, swept under the rug. Another great question then, and something that I see a couple of people have jumped onto, and that you yourselves have said, kind of, yes, let's answer this. Could you talk a bit more about breathability versus air tightness? As usually natural materials are associated with being able to regulate air quality and transfer humidity between inside and outside, and a bit of uncertainty as to whether this is the case with an airtight barrier.
Very glad you moved on to this one next, because I'm keen to talk about this. Yes, absolutely. So yeah, natural materials are breathable, generally speaking, which means that humidity, not air, can sort of pass through or self-regulate through the material. And breathability is a sliding scale. It's not black and white. So that's the first thing to understand. But so something like the wood fibre board is highly breathable. Wood is very breathable. As we come to the sort of OSB boards, which are more engineered and have some glue in them, less breathable, as we discovered by the lack of the drying out of the light earth, and that was interesting, because we thought it would be more breathable than it was. The smart ply, the airtight layer, definitely is a lot less breathable. I think it's supposed to be technically not vapor closed, but it's not what I would classify as a breathable material, even though it's on wood. It's not doing a lot of breathing, which is a shame, because obviously you've got the rest of the building is made up of breathable materials. And had we gone with, say, straw makeup, like the ACAN system, they have a breather membrane as well. No, it's the airtight. It's still an airtight membrane, not a breather membrane. It's the airtight membrane. It still has to be there in order to get the airtightness effectively, and that has got to be made of something. I think the paper-based one, which I forget the name of, but I think that would be very interesting to understand more about the breathability of it. But what I think is really interesting is the fact that we're using, yes, we have this airtight layer, which is reducing the breathability from that point, but on the inside of that, we have this quite significant layer of clay plaster, which is hygroscopic. And so we are, even though we're not necessarily getting the breathability with the outside benefits of the wall, we are getting the hygroscopic benefits of the clay and the natural materials as finishes internally. So our internal humidity and air quality is very much still regulated by those materials. There's a lot of absorption and desorption of moisture happening internally. It's just not necessarily passing through. And I think that's quite interesting in terms of the ventilation system, because a lot of ventilation requirements, ventilation is needed for three things: fresh air, but also to remove humidity, excess humidity, and toxins. And we have pretty much tackled those two by having very good internal humidity, internal regulation of humidity, and by having next to no toxins. We're also not having things like new carpets inside, which are a big emitter of VOCs. We're using clay paints and a lot of secondhand things. Which, yeah, you were going to say that.
Yeah. A secondhand material has got like an added value because it's already done a lot of its off-gassing. So it's it's even better from a health perspective.
Yeah, exactly. So yeah, using a lot of reclaimed things. So we're really having a lot less toxins. So we just really need the ventilation for ensuring we have enough fresh air, enough CO2, and that's something that we're monitoring. We've got monitors. Obviously, we're gathering lots of data on many fronts, but CO2 monitoring is one of them as well. And I think that's going to be very interesting to look at the actual ventilation requirements from the modelling versus the reality of living in a sort of natural passive house.
I think a good point has been made in the chat about the phrase vapor open as opposed to breathable maybe needs to enter more common parlance, because it makes that distinction and clearly draws the line. Otherwise, we are confusing two very different processes. So that helps introduce clarity. One that, while we're on the topic of natural materials, perhaps, and a couple of people have asked questions around it, if I just say the two words fire safety and perhaps let you run from there.
What was the second one? Fire safety and?
No, that was it, the two words,
Oh,
fire safety.
just fire safety.
Fire safety.
Oh, is that all?
Just that little topic around natural insulation and natural materials.
Yeah. Do you want to talk about that, or shall I?
Yeah, sure. I'll talk about it a bit, and then you can jump in and save me. Yeah, I'm glad that people asked the question, and it is something that through ACAN has kind of like tried to simulate conversation around talking around fire, because natively we're not taught about it at university. Yet we have to deal with it every day on a on a job basis. So I think we're in a harder situation than when we started the project because of the Building Safety Act. And positively, the Building Safety Act, which was brought about because of the Grenfell tragedy, has been driving an increased level of rigor in building control, which is what it was aiming to do. What's quite interesting, though, is that there is not sufficient information in the industry to support the level of rigor that the Building Safety Act is calling for. Ideally, what building control would like to see is certificates of all of the products, not materials, that you're using in the building, and you would need to demonstrate that you are not diverging from all of the limitations of all of the fire certificates for all of the elements that are providing anything to do with fire safety, which is incredibly onerous, and I've talked about it in great lengths elsewhere online, Google. So big divergence is that we're using materials and not products. And when we've spoken to building control about it, they've accepted that you can use materials and not products, and they've accepted that you can never have all of the certificates of the materials and not products, because they're materials, and by their nature they're specific to your site and your instances, and your clay is different from everyone else's clay, and have said that ultimately it's down to their decision based on the information that we can provide to them. So we have gathered a lot of existing information from as closely relatable details and build-ups as possible to ours, which have got quantified fire performance outcomes, and it's going to be with building control to decide if that's appropriate and sufficient or not. Obviously, we've satisfied our own kind of what's the word? We satisfied ourselves, exactly. Yeah. But if building control aren't happy with the information that we have, then ultimately you're talking about testing, which is something we have started talking to them about. But it's completely impossible for every project to seek to test everything that they're going to use, because there aren't enough fire test labs in the UK. They're not tall enough. We don't have enough money. We don't have enough time. So as an industry, we've got a long way to go, and we need to really move towards having an open source platform for sharing the fire test information that exists, because there's loads out there, but it's held behind walls because of the intellectual property that's associated to them. You've got to sign non-disclosure agreements. They won't give them to you. So the industry is going to have to go through a big step change. And yeah, we've been at the sharp edge of that on this project.
I think I would like to add that it's slightly ironic that the last time we were giving this talk in London was when the building control officer came round as a sort of surprise visit, and then wrote us a letter saying we've got mud on all the walls and that could be a fire risk. And
industrial straw.
Yeah, agricultural straw. Yeah, as opposed to anyway. So yeah, we have now got to provide this information, which basically is because he's not familiar with clay plaster. He's never worked on a building with clay plaster before. So yeah, we're having to walk him through it. And although it's another thing for us to do, I'm kind of glad, because we can document how we're going to get him on board, and then share that information with all of you and everybody who's doing similar things. I'd also like to say that we have 100% confidence in clay plaster not being an issue, because clay doesn't burn. In fact, it's one of the few materials that gets stronger in fire. It's an amazing material, and there's a lot of test data out there on various other buildings. I mean, it's been around for a very long time. There's a lot of information about it being used historically and how it performs in fire on all different substrates. And it can provide, I think it's shown over 2 hours easily of fire resistance. Obviously, it varies depending on the thickness and things like that, but and the substrate and the fixings of the substrate. But yeah, it's also, yes, as George has just said in the chat, straw doesn't burn either. I must just put that in there, because compressed straw is very dense and doesn't burn. So even if it didn't have clay plaster on it, it still wouldn't burn. Not that our house is straw bale, but I'm just saying that because that is something that people often ask.
We also we're using some alternatives to plasterboard behind the clay in the stairwell, because it's going to be a 3-story house, and then so you need a protected fire escape stair. So we are using boards that have got cast data behind the clay in the stairwell.
Yeah, we've got some Honex boards which are made of waste paper from an ACAN event, in fact, because they were via a future build event. We managed to get some of these boards for free, which was and they're really good. So yeah, we've got a mix of different materials, and we're going to try and record. So we're doing a lot on well, I'm not very good at social media, but I'm trying to record what we're doing. I'm trying to put lots of posts up and share information about all the different ways that we're doing things like the plastering. I have no concern at all about fire or moisture, but we will be trying to get our building control officer on board on that, and then we'll share what happens.
That's brilliant, thank you. Maybe I can just, on the back of that, and it should hopefully only be a very short answer, ask where you used the cork. Because that was in one of your original slides, but...
I have actually used it, little pieces of it behind the MVHR plenums. So the inlets and extracts into the room, particularly
natural acoustic dampness.
As acoustic dampeners, exactly. So we've just put a little piece behind that, so it's fixed through that to the timber floor. So our bedroom, for example, is above the kitchen, where there's an extract below, and that's fixed to the floor effectively. So having that acoustic dampener is really useful. We're also using it in the reveals of the windows and doors. That's what I'm planning to do, but haven't yet. Come along and volunteer, use it together.
I think we'll be doing another shameless plug for that, don't worry. Back to the geekiness of moisture and data and all those wonderful sensors that you've installed throughout your construction. Has that process, and have the recordings that you have to date, and of course the recordings you'll have for presumably another 9 years, 9.5 years, till those batteries die, has it given you an insight into how to manage internal solid wall insulation in existing or heritage buildings and possible issues there with internal condensation or moisture?
I saw that question in the chat, and I didn't reply because it was a complex one.
Yes.
I mean,
it's going to perform a little bit differently.
Yeah, it would. I mean, I think it's a very different conversation. I would definitely encourage the use of sensors on any project in the future, and at work we're putting it in the specification for all of our projects. They've got to be screwed into a wooden substrate, but you can put that anywhere in your build. So I would definitely encourage the use of it to see how how it performs. But I also appreciate a retrofit of a building is a very different situation, and it's really important to do some good analysis to understand how that system's working before you start intervening with it. Absolutely. And do some environmental monitoring beforehand. Andy mentioned the thermographic camera, really useful when you're working with fabric to see is it actually a consistent wall build up all the way through or not, and opening up works. And what we do at work is we make sure we measure all of those things and then make a PHPP of the existing building to understand how it's working, and then you can model your fabric interventions to make sure that you're not going to be introducing too much insulation that then can lead to interstitial insulation risks.
Yeah, particularly internal insulation can have that risk, or external if it's not breathable.
And not complemented by an appropriate ventilation strategy. No, that is great. Thank you. And maybe it just relates to the fact that, again, there are certain things that we need to get better at generally in practice. And one of those is post-occupancy or in occupancy, if you've got an existing building, evaluation and that data, that monitoring, getting more conversant with these devices and with the interfaces through which we can analyze the data. So thank you. I'm aware that we are starting to run a little bit close to the end. Maybe we'll do that other question that you perhaps answered as being too hard in the chat. What are you using for heating?
Oh yeah, sure. Yeah, so Tab will love this one. Passive homes need a tiny amount of energy to heat. So the mechanical ventilation heat recovery captures over 90% of the energy of the air that is expelled from the house, and it transfers that into the fresh incoming air, which means you only need to add 1 or 2 degrees of heat to the external air, which means you need very little amounts of energy. Now we were like, well, we'll use an air source heat pump because there's a $7.5 grand grant from the government. The smallest heat pump you can get is it's like a bigger unit that runs down at 4 kilowatts. And the max heat demand of our house is 1.8 kilowatts, which means you would have to have a very inefficient system. And then we were told that actually to defrost an air source heat pump, you need to take energy from the house and run it through the pipework every 45 minutes to defrost. So actually we're talking about using the house to heat the air source heat pump. So we decided in the end to actually just use some direct electric radiators. We only need a couple. I've got friends who live in passive homes and they just use a heated towel rail. And that's what we're going to be doing. We actually have the pipework in for a wet radiator system because we'd already gone too far. So we've kind of material banked some copper for the future.
Does anyone need any copper?
But yeah, so we're just going to have some electric radiators around the house and it will be fine. We are going to use a direct electric, probably water cylinder. We might use an air source cylinder. And then we're going to have PV, and yes, that is higher carbon than using other solutions, but it's exceptionally, it uses a lot less technology. You haven't got refrigerant leakages from air source heat pumps. You haven't got all the material that goes into making it in the first place. So that's what we're choosing to do. It's a very divisive topic in the kind of in the sphere. And there aren't, market-ready solutions for heat pumps for passive house heating demands that we've come across that people are happy to install and to size to, because a lot of people don't believe that a passive house uses as little energy as it does. And that's also been a kind of learning journey with people we've spoken to, which has been very challenging.
Systems are sized, not taking anything into account to do with heating, the actual heating demand.
That's great, thank you. And I see George has comment. Sorry.
No, it's actually originally I had always sort of wanted a fireplace and a log burner, and that's something that to me it's like a part of the house, and I was really it's like a farmhouse. It needs a fireplace, right? But yeah, that's one of the things I've come around on with Passive House is understanding just how ridiculously unnecessarily expensive that would be for something that we've never used.
The poor air quality that you get
and the
particulate matter. Thank you, George.
George helped persuade. Also, Seb made the point that on those really extreme cold days when we get a really, really cold snap, which I'm foreseeing in the future we will get, just invite everyone over.
Housewarming.
We all have 100
housewarming, exactly.
We all have 100 watts coming off us.
Just invite the whole Passive House community, which perfectly segues actually, because I want to abuse my position and ask a question. So if I may, and I won't actually make this the final question, I'll ask one more afterwards, which has been put in the chat. Will you be hosting visitors for the Passive House Summer Open Days 2025? That's a thumbs up. That's a yes.
We did it last week and we'll do it again this year.
Fabulous. No, that's wonderful. And the other question then off the back of that, which again, lots of people seeing your inspirational sketches, photographs, story are asking, how do they get involved with volunteering, please? Where can they go?
Yes.
Apart from to your house, obviously.
Yeah, just turn up. I mean, no, don't. I think the best way is probably, so we've got a website, which is llama-croft.com. Or we're on Instagram, which is llama_croft_HR4. Or Seb's on LinkedIn. I don't really do LinkedIn, so I don't know how that works, but he's on there. Find him. Message us, and then we can send you a link for the volunteer group that we set up, and you can join that. I don't want to make it too public so that everyone joins too easily, because yeah, that could get a bit much. But we have got a good number of people who are volunteering most weekends, and weekdays too is very welcome. So yeah, do get in touch, and there's so much more to do. We'd really love some help. So yeah, and even once we're done with the help, we do always love having visitors, and we can talk about our house for hours and hours. So yeah,
particularly on freezing cold days.
Absolutely, come and help heat our house.
Wonderful. Well, with that, I would like to draw this session to a close. So thank you again, everyone who has remained to the death, for joining us this evening, and a special thanks to our wonderful speakers with their wonderful presentations. Thank you, Tab, clapping along. You can access more presentations in the ACAN YouTube channel. You can get involved in conversations via the various thematic groups. And you can find out about opportunities for volunteering with ACAN and so much more on the website, which has been put at various points in the chat. If you're not already, please consider becoming a member of ACAN. All details are again on the website, and I'm guaranteed it costs less than a London coffee. And if you would like to continue the session after this session at the ACAN Open Arms, please follow the link in the chat. Thank you all so much, and have a good evening.
Thank you.
Thanks.
Take
Thanks,
care.
everyone. Bye.